Okay, welcome to our final project about deep learning models for stock trading for IST691. I'm Bo Spratt. I'm joined by Matthew Smith, Matthew Spitolnik, and CTS Stable. This is what we're going to talk about today. I'm going to go over CNNs, over synthetic images. Matt's going to talk about deep learning with Elliott waves. And Matt's going to talk about text mining and stock price increase prediction. And Cynthia's going to do some reinforcement learning for portfolio trading and LSTM combination. So we're basically trying to use deep models on our approach to these different stock market predictions that we're making. And we're using indicators and deep learning networks with lots of layers and nodes. First is CNN over synthetic images. So we're predicting here next day and next minute closing prices using like the past 100 months for the day-to-day or the past 7 days, because that's kind of the data that was available. So from Yahoo Finance, as I said, the 100 days or 7 days is what we chose. And these are the different technical parameters or indicators that every stock has that's traded on the stock market. And these are all the parameters I had to do during testing of all of my models. You can see it gets kind of pretty crazy. So here's an example synthetic input image where the width of it is the time, which would be 20 days or 20 minutes. And you can see all the indicators as rows to this image. And it's normalized from 0 to 1. And the idea comes from an article that Cynthia sent me about predicting stock markets using images. Some of the future additions I would add to this, if we had more time, is some of the Fibonacci, the volume indicators, news, average, true, false range, and a concept called social shadowing, where you kind of copy other people's trades. So here's the model I used for my CNN. It's got a convolutional layers, it's got pooling layers, and it runs into a flattened layer in order to use some LSTM and some dense layers at the end. And it's going to be predicting closing price, as we said. So for an example, I put it like in 2,000 images were sent in, and the model had 67,000 parameters when ran. Here's some of the example outputs and how I really want to emphasize how each stock, as you input into the model, reacts differently. So some stocks really react to their these indicators differently than others. And you can see how the training was much more fuzzier, it required more time or less time according to which stock was put in. And here's our results. And as you can see, for a stock like Apple, we only got like 1.1% error, but a stock like GameStop at the bottom, you got 13% error. So you can see that these are not really following their indicators. But you can see the first column there is mean squared error. That's how many dollars we're off. And the second column is that as a percentage. And then the third column there is like how accurate we were over the course of a week or over a course overall. And 64% and 51% for Apple, which is also telling you not to invest this in real life, this is just a model. So if you compared that to random forest, Apple got a mean squared error of 5.18, which is a lot worse. So it kind of shows that this is a unique technique to use, and it kind of helps. It's helpful and improves your results. You can see the relative importance in random forest of each of the features that were in my synthetic images and how that changes per stock. As you can see, Tesla and Apple have different feature importances. So as we said, there are tons of parameters to optimize for each stock. Each stock reacts differently, and several features can be added to one image so we can make large images. Fast training times, which was nice in this testing, and it improved results over basic models like random forest. So it's got a lot of future promise. Next will be Matt Smith talking about deep learning with Elliott waves. Thank you.
Yep. So the approach that I took was to take a particular set of features within stock trading called Elliott wave theory. Basically, the premise is that a series of peaks and troughs, basically the high points and low points during certain periods or within a certain window, can be indicative of the trend that the price will follow. For this, we created different features: peaks, troughs, wave statuses, one being a trough and two being a peak, and also calculating the wave length and wave amplitude. These are the different stock tickers that I use: NVIDIA, Tesla, Apple, Amazon, and Microsoft. First model architecture I used was a convolutional neural network plus LSTM layer, similar to what Bo had run. However, I decided to go with the tan-H activation function, as that, at least in my application, gave me a lot more success here. And I was taking a sequence of 48 data points and outputting the next 12 hours. Input of 48 time steps to output or forecast out 12 time steps or 12 hours. I also used a CNN plus GRU architecture in order to compare the performance of GRU layers versus LSTM layers in this instance. Same thing as before. I was still taking 48 times, inputting 48 time steps to output 12. So for these results, the best one that the best results between LSTM and GRU for NVIDIA actually ended up being the GRU layers with root mean square errors of 22 as opposed to 53. Even though the points don't match up as they don't match up equally, like on the right hand side for the actual predicted points, but the pattern does seem a lot closer rather than nothing at all. Here we saw a root mean squared error for the Apple ticker of $3.82 using the LSTM layers in this instance. In this instance, Apple actually reacted better to the LSTM layers as opposed to GRU. However, best overall out of every experiment that was run was Amazon using the GRU layers with a root mean square error of about $2.88 prediction error. And as you can see on the right, even though the points don't match up exactly, the patterns are pretty dang close for only using about 50 epochs for the training cycle. Next, after using pretty straightforward model architectures, I was finally able to get the generative adversarial network running for this data. Basically, having a generator model and discriminator model both running GLU layers. However, it didn't really produce very useful results. You can see during training losses, the generator and discriminator were basically battling it out and started to level out towards the 1000th epoch. And as you can see toward the bottom, the generated data on the right hand side of that facet plot wasn't really looking anything like the real data for that sequence starting at index 0. But for this model, there was a paper that I was reading where they were using ARIMA features. Instead of using the actual ARIMA model, they just took the features from it and fed it into the model in order to get it more time, give more time series features to it, using a Fourier transform as well as a sliding window. Attempted to use these in my model, however, prior to this, however, it was taking a lot more computational power than I had. So that would be more of a feature piece for exploring this kind of architecture. So conclusions, CNNs for LSTMs versus recurrent GANs. Different stocks reacted differently between the LSTM and GRU-based models. Amazon had the best with the GRU model, and Apple actually had the best error with the LSTM model. Single model methods turned to perform better than the vanilla recurrent GAN model that I created. However, it was either just not the right adjustments or not enough time or computational power to train the model properly or for as long as it needed to. And I'll be followed by Matthew Spitolnik.
Thank you very much. So for my portion, I was looking at whether or not we could use text data to potentially predict what would happen to a stock price. So more specifically, what I did was I collected a whole bunch of news articles about stocks and then wanted to see if the, based on the opening price the day that an article came out, if we could predict if it would go up or down the following day, the following market open day. So to do this, I used a few different sites to get a big list of trending stocks at the time of about 500 different stocks. I then used that to feed into a function that scrubbed a whole bunch of news articles and then used Y Finance to then collect the stock prices from the dates that the articles were released. And in the end, that ended up with 8,740 articles that were talking about 325 different stocks. And so to build it, this is the base model that I started off with just an embedded layer that fed to LSTM with a dropout layer, followed by the dense layer with an activation. And so that's just the very base model that I started off with, and then I did a bunch of different variations of it to test a few different things. So this is a bunch of the different things that I was messing around with. So I was working with the raw text data that I collected versus pre-processing it. Changing the amount of words, that the max number of words that would be allowed in each article that was fed into the model, the number of words or features that could be indexed, the size of the test data, whether it's going to be 70% or 80% of the data that I was using for training versus testing. For the embedding layer, I was using self-trained layers versus pre-trained layers. So I was using, I tried out the Glove pre-trained embedded layer and the fast text pre-trained layer. I tried out with masking without masking, and I was changing the output then from the embedded layer. I mixed up the number of units that the LSTM layer was using. I tried it with and without CNN layers. I added in a second dense layer. I was trying out different activation functions, some different optimizers, I was changing up the learning rates and regularizations and different number of epochs and validation splits. So when it came to the pre-processing, this just kind of shows what the data looked like with and without the pre-processing done. On the left, you can see the number of words per article without the pre-processing was about 408 words versus after it was processed, it was about 193 words. There was, I removed stop words, contractions, removed numbers, removed the name of the stocks, pretty much anything that wouldn't be considered significant. And this just shows the words that were showing up the most throughout the different articles. So you can see company, NASDAQ, New York Stock Exchange, words that we'd expect. And then that's the blue bar, and then the orange bar actually shows how many of the articles the word showed up in. And then this, just for comparison, again, this shows what that would have looked like if without the stop words taken out. So you can see, the shows up the most at 174,000 times, and it's in 8,500 of the 8,700 articles. You can see the other words, are all stop words, common words that don't really add much usually to analysis, like to, of, and, in, etc. So overall, after all the different variations were done, these are what the top 10 models came out to be, with the best one being the top one with a test accuracy of about 65%. Some things to notice: all of the best models did use CNN. They were all self-trained. None of the pre-trained models were working. And the learning rate you can see in all of them is lower than the 0.001. That's the default for a lot of the different optimizers that are out there. One thing that's also interesting to see is that you can see that one of the models was not cleaned data, and it still was one of the best accuracies, which I'll briefly talk about in a little bit also. So this ended up being what the overall best model was I showed before. It was self-trained, like I said. The 150 words per article is what the limit was. We were using 2 different dense layers with a few different activations. The big thing was the learning rate, once again, was lower to 0.0001 as opposed to the 0.001 that a lot of the optimizers use. This shows of all the different variables that are changed. This kind of shows the correlation that was going on. If you look at the learning rate, you can see that's 0.0. You can see that's a negative 0.43. And that's because actually, as we lowered the learning rate, the accuracy actually went up. Other thing to notice is, once again, with the CNN underscore fact, that means whether or not there was a CNN layer, and it's negative, but that's actually because it's a yes and a no, and the yes was labeled as 0 and the no was labeled as 1. So it shows like it's negative, but actually, as you add the CNN layer, the accuracy goes up. And so just to reiterate the learning rate accuracy, the models were showing a lot of signs of being overfitted. And so lowering the learning rate helped to fight that. And you can see here, the blue line is, these are the exact 2 same models, except for the learning rate change. And so the blue line is the model with the learning rate lowered to 0.0001. And you can see how quickly, almost at epoch 7 or 8, it's up to 90% accuracy, as opposed to the model with the learning rate that's at 0.001. It doesn't get up to 90% accuracy until almost in the 30s, and then it keeps on dipping up and below it. And the model that was 0.0001 stayed up above it for almost the entire time after that. And then this isn't as drastic of a difference, but you can still see the difference here. Once again, this is with the exact same models, except one's using CNN, one is not. You can see that the model with the CNN gets up to 90% pretty quickly and stays up there. The red one still performs almost as well, but you can still see the clear difference in the performance of the blue CNN model. So different conclusions. Using the self-trained embedding layers definitely increased the accuracy, but it also made the model's performance go down, and it took a lot longer to run. So that became kind of an obstacle. Combining the CNN and RNN layers with the embedding layers definitely did improve the accuracy. The reducing the learning rate definitely helped with the accuracy also, and helped to avoid some of that overfitting, although none of the performances were amazing, because 65% was the highest we got, but we could definitely still see a difference. Cleaning the data did help with the performance, but I think a lot of that has to do with the performing power of my workstation. I think with a workstation that was stronger, that could handle having all of the data in there and could have max length windows a lot bigger, so it's looking at more words per article, I think raw data would perform just as well, or potentially even better, because you might be able to see more patterns in the raw data than you can see in data that's been pre-processed. The allowing for too many words, at least with the clean data, did not necessarily result in better accuracy. And I think back to the football field analogy we talked about in class, where if it's too, if you make it too small, then you're not going to get a good enough picture. But if you make it too big, then there's too much to work with. So I definitely think I saw that at least with the cleaning data or the data that's been cleaned. And overall, I think to actually get this model to a place where it could be used, I think a lot more granular data would be needed. For example, looking at the exact time of day that an article came out, because if it came out at 6 o'clock after close, that would make a bigger difference than if an article comes out, or if article comes out at like 9 in the morning. And seeing like if an article comes out on a Friday, obviously when you have 2 more days in between that and the market open for people to digest what's in the article, that's probably gonna make a big difference on price too. And now Cynthia is going to take us home.
So continuing with our exploration of deep learning models for stock trading, we also toyed with the deep reinforcement learning model, DRL. Previously, we've been focusing on predicting stock prices using supervised learning methods in combination with other machine learning models and several different technical indicators, all with the ultimate goal of trying to forecast the next closing price. With DRL, our approach has to change. Instead of a mere next close prediction, the DRL model will actively learn from the market, and based on the environment, it will make strategic decisions on its own. Basically, it will make the decision to buy, sell, or hold the stock in order to maximize its profitability. So each decision or step is influenced by rewards, which provide feedback to the financial impact of the actions taken, similar to when a player is changing its strategy to win the game or win a game. I used the DRL model to analyze NVIDIA stock using daily data from January 1st, 2021 to November 2023. The model score, or DQN agent, is structured as follows. An input layer with 24 neurons designed to process various features of the stock, 2 hidden layers, each with 24 neurons for extracting and learning, ReLU activation functions following each layer, introducing nonlinearity as well to enhance the learning process, and final output layer with a number of neurons equal to the available actions, which in this case is 3 for buy, sell, and hold. The agent's role is to make stock trading decisions, as I mentioned before, based on the current state, which includes the historic data, the entire period. So as it learns from its actions, it will update its profitability in the form of rewards, and they in turn get calculated in the form of gains or losses throughout the entire process. So the decision-making process of the agent is guided by this epsilon greedy policy, which initially the agent explores its actions randomly, and as it gains experience, the epsilon value decreases. So the agent it will increasingly rely on its learned knowledge and shift focus from exploration to exploitation and exploration back and forth. Next slide. Now, looking at the same model over 500 episodes, we see that there are some modest improvements in profitability as the model reaches, in a few instances, about $700 in total. It is progressively learning, which is what we hope it will do. So next, we added several new features in the form of technical indicators to see if it would help the model improve. As it turns out, it didn't. Instead, it did not make a profit at all, and over the same 500 episodes. So it also significantly reduced the overall number of trades. The epsilon decay chart shows it spent more time exploring rather than learning. With these many features to explore, perhaps a much larger number of episodes and the size of the data should be increased for us to see, some significant improvements. So for comparison purposes, here's the same data set using a non-complicated LSTM model. Over the same time period, this model would have made $5,300 in profits, indicating that sometimes sophisticated is not always the best option. So what would happen if we combine LSTM, the LSTM next closing price prediction to the DRL environment? Turns out, not much at all. Going back to the first example with using the 100 episodes over the same NVIDIA stock, the results produced a maximum return of just over $550. So what would happen if, what would DRL plus LSTM look like over a portfolio of stocks instead of a single stock? So if you look at the chart in blue, these are the combined returns of all 5 stocks that you see there: Apple, Microsoft, Google, Amazon, and Tesla. In the overall combined rewards were a total of $750. And here we're just showing 20 episodes, but as you can see, it's following the same pattern of just staying with low profitability. And each of the stocks has its own pattern, but still not enough to justify using it. By contrast, the LSTM model only without the DRL for the same stock, same time period. In this portfolio, the stocks produced about $22,000 in profits. So clearly, there's a lot of work to be done to get the DRL working the way that we need to. And the next slide, we'll go over some of these suggestions. So in conclusion, the DRL successfully learned to make buy and sell and hold decisions based on its environments. Increasing the number of episodes slightly improved the overall profitability. More features did not necessarily produce better results. When combined with LSTM, it significantly increased the complexity and it took a lot longer to train, but in turn did not improve the results. So employing multiple agents in a portfolio setting also did not produce better results as we would expect. Next steps, probably further exploration using larger data sets and combining other techniques such as encoders could be something to try. And this concludes our presentation. Thank you.